Hi everybody, the purpose of this video is to go over section 3 of chapter 2, and we will be talking about functions. First, we will talk about relations and functions and their similarities and differences. We will then discuss the domain and range of both relations and functions. We will go over a very critical test, which I believe you've seen before, to determine whether a relation is indeed a function or not. We will reintroduce function notation, and we will talk about the interpretation of a graph by determining where it is increasing, where it is decreasing, and other important properties of a given graph. Okay, so here we go. What is relation? A relation is nothing more than a set of ordered pairs. Now, sometimes this set can be a finite collection of ordered pairs. Sometimes it can be an infinite collection of ordered pairs, or sometimes it could be a uncountably infinite collection of ordered pairs, which is sometimes best represented as either an equation or a graph, which we have right here. So really, this right here is nothing more than a visualization of a collection of ordered pairs, which are uncountably infinite. And this right here is an algebraic representation of the same set of ordered pairs. What is a function? Well, a function is a relation, so it's a set of ordered pairs. But it is a set of ordered pairs that is well defined. And what do I mean by that? What that means is for every single value of the first component, or more importantly, for every single input, there is exactly one output, or exactly one value for the second component. You cannot have two outputs associated with the exact same input. For example, here, in this relationship right here, which is basically a unit circle, notice that when x is equal to 0, if your input is equal to 0, your output can either be 1 or minus 1. So we actually have two outputs for the exact same input. So this is not a function. Okay, so how do we decide whether a relation is a function or not? Well, if we have just simply a collection of ordered pairs, we look at all the x values. And if the x values are all different, if the first coordinate, or once again the x values are all different, like they are here, then we have a function. Okay, so this right here, f here, is a function. On the other hand, if the first coordinate repeats, like here we have a 1 here, a 1 here, a 1 here, so we actually have 1, 2, 3 different outputs for the exact same input, then this relation cannot be a function because it is not well defined. Why is it not well defined? Because if you put in a 1, you don't know if you're going to get you don't know if you're going to get a 1, 2, or a 3, and that is not well defined. It would be well defined if you put in a 1 and you only got a 1 out, or one of the other ones. So this is not a function. Okay, so in a function, no two ordered pairs can have the same x value in different y values, and that is primarily why g here is not a function. Same x value, different y values. Another way of saying that is that in a function there is exactly one value of the dependent variable, or one value of the output, for each value of the independent variable, or for each value of the input. Okay, and here is another way of looking at the function. Here's our input. What comes in here is what we call x, or what we call the independent variable, and what comes out, well, we call this the dependent variable. Why? Because whatever the output is depends upon what you put in. So once again, the input we tend to call x, and it is the independent variable, and the output we tend to call y, and we know that as the dependent variable. Okay, so what is the domain? Well, the domain is the set of all possible inputs, or all possible independent variables. And the range, well, the range, as you might guess, is the set of all possible outputs, or the set of all possible dependent variables. In general, if you have a function described by an algebraic expression, what do you mean by when I say that? If you have a function which is defined by an equation, then the domain is going to be all real numbers except those that cause the equation to be undefined. And when does that occur? That occurs whenever there is division by 0, or whenever you have an even root such as a square root, and the argument happens to be a negative number. Because if you are restricting yourself to the real line, then the even root, such as the square root of a negative number, does not have a solution. And what is another way of testing for a function? Now, the first test that we talked about, just looking at ordered pairs, is great if you have a finite collection of ordered pairs. However, if you have an equation or a graph of an equation, you need something else, and that's where the vertical line test comes in. So if you have a graph, you can actually, if you have a graph of an equation, you can apply the vertical line test. And what is that? Well, you pretty much superimpose a vertical line, and if that line intersects the graph of the equation at more than one point, then that equation is not a function. And all you need is one value of x where the vertical line intersects the graph of the function twice, and then it is not a function. So here, once again, here's our unit circle, and as you can see, that if the vertical line is here, it intersects up there and down here. Sorry for those technical terms. So this clearly is not a function. However, this graph right here, which by the way is a graph of a sine function, which you will learn if you ever decide to take pre-calculus. Notice here, any vertical line you draw will hit the graph of the function exactly once and no more. As a consequence, this is indeed a function. Okay, so let's put this to the test with example 4. Here we have a collection of graphs, and we want to determine whether that graph represents a function, and whether it does or not, we want to write down its domain and range. Now remember, the domain is going to be all of the inputs, which is the first coordinate. So here we have essentially just this function. This relation consists of 4 points. Here's the first point, and the input there is a -1, or the x-coordinate is a -1. Here we have a 0 in the first coordinate. Here we have a 1 in the first coordinate, and here we have a 4 in the first coordinate. That is the domain of our function. The range is the outputs, or the second coordinates, and for that one we would have a 1, a -1, a 2, and a -3. Does this relation represent a function? Well, it turns out, yes, it does. Here this vertical line intersects the graph once. It intersects the graph once here, as well as it does here as well. However, here it does not intersect the graph of the function at all, and that's perfectly fine. The criteria is that it has to intersect the graph at most once. And here it intersects the graph once, so yes, this is indeed a function. Okay, what about this one? Well, notice this vertical line hits the graph twice, so this is not a function. But it still has a domain and range. Notice how in terms of x values, the x values range from -4 all the way to 4. This graph covers x values from -4 to 4. As a consequence, that's what its domain is going to be. The closed interval from -4 to 4, including 4. And notice the outputs range from -6 all the way to 6. So that would be the range. And once again, our range will be the closed interval from -6 to 6. So we have domain of -4 to 4, closed interval. The range is the closed interval from -6 to 6, and this is not a function. Test. Now what about this one? This right here is a standard linear equation. Notice that for any vertical line will hit this exactly once. So this is indeed a function. What is its range? Or I'm sorry, what is its domain? Well, notice it takes all values of x, so the domain is going to be the real line. And you can see that just by following the arrows. And it takes all values of y, so the range is also the real line. And this is true for any linear equation. And then finally, here is a graph of a quadratic equation. Is this a function? Well, yes, it is. Notice that any vertical line will hit the graph exactly once. What is the domain? Well, notice here that this will continue all the way down to negative infinity for x, and this will continue all the way up to negative infinity for x. So the domain, once again, is the entire real line. But as before the range, notice that this graph has a minimum value. That minimum value is 3. The outputs will never be lower than -3, not 3, but -3. So the range is going to be the half open interval, which starts at our minimum value of -3 and goes all the way up to infinity. So that would be our range, and yes, this is indeed a function. Okay, now let's take a look at some algebraic equations, and determine whether they are functions, and also determine their domain and range. And here's our first one. Here we have y is equal to 2x minus 1. And sometimes it helps to actually graph the equation, and here's the graph of the equation. And notice that this will pass the vertical line test for any value of x. So this is indeed a function. What is its domain? Well, the domain is going to be all values of x where 2x minus 1 is greater than or equal to 0, because we can't have any negative square roots. And of course, if we solve for x, we are going to have that x is greater than 1/2. So the domain is going to be all values of x such that x is greater than or equal to 1/2. And however, your answer will probably you'll need to specify this in interval notation, and that would be the half open interval starting at 1/2, including 1/2, and going all the way up to infinity. What is the range? Well, we can tell this from the graph. Our lowest value is going to be 0. And then your outputs will increase all the way up to infinity. So your range will be from 0 to infinity. Okay, this right here is not a function because this fails the vertical line test, because we have an intersection here and an intersection there, so this is not a function. And you can also tell that, and you can also come up with two ordered pairs with the exact same value for x, which will make this statement true. So if x is equal to 4, and y is equal to -2, this equation is satisfied because y squared would be 4. And of course, if x is 4 and y is 2, this equation is still satisfied. So this also shows you that this is not a function. Now, what is its domain? Well, notice here the graph starts at 0 and goes all the way up to infinity as far as x is concerned. So the domain is going to be the half open interval from 0 to infinity. And then the range, well, notice here that the outputs can go all the way up to infinity and all the way down to negative infinity. So the range will be the entire real line. Okay, here we don't have an equation, we have an inequality. And as you can see, well, everything shaded here is a solution to this inequality. So this is not a function. There's no way an inequality can ever be a function. However, it can still have a domain and range, and since this is actually a linear inequality, it turns out that the domain will be the entire real line, and the range will also be the entire real line. I guess I should have included the equal sign there. And then finally, let's take a look at this one. Now notice that this equation here, which is a hyperbolic equation, or also a rational equation, passes the vertical line test at every single point. Even when you get close to where this thing is very, very large, it still only intersects at one point. So this is indeed a function. And since this is an equation, the domain is going to be the entire real line except those points where the denominator is equal to 0. So notice here that the denominator is going to be equal to 0 when x is equal to 1. So the domain is going to be all values of x except for when x is equal to 1. And how would you write that in interval notation? Well, that's going to be the open interval from negative infinity to 1, that we were not including 1, and then we are going to union that with the open interval from 1 to infinity. That gives you the entire real line with the exception of x equals to 1. What is the range? Well, notice here that the equation takes on all possible values except 0. It never quite reaches 0. So the range here is going to be the open interval from negative infinity to 0 unioned with the open interval from 0 to infinity. And there you go. Now we want to talk about function notation. And function notation is basically just another way of expressing the variable. Essentially what we're going to do is we are going to make our y, we're going to replace our y, our dependent variable, with this thing called f of x, where f is the name of the function, okay, and then x is the independent variable. And when we set this equal to something, that equality is going to be the rule that we will apply to the independent variable x. And when we read this as f of x. Okay, so for example, suppose we have the equation y is equal to 3x minus 5. What we're going to do is we're going to replace y with f of x, and then we have f, which is a function of x, is equal to 3 times x minus 5. So whatever we replace x with, we are going to follow this rule. We're going to take whatever goes in here, multiply it by 3, and then subtract 5 from the product. Okay, for example, suppose x is equal to 2. Wherever we have an x in the rule, we're going to replace that with 2, noting that this implies multiplication because we don't want to think that's 32. So if we have a 2 in here for the argument, the rule is going to be 3 times 2. Okay, we're going to take that product and we're going to subtract 5 from it, which will give us 1. So we have function f evaluated when x is equal to 2 will be equal to 1. Okay, and once again, f of x is just another name for the dependent variable y, and we are not talking about times, but it just represents the y value for the associated x value. Okay, and this once again is a breakdown of the function. This is the name. That's the independent variable, and and once again, y and f are pretty much the exact same thing, except now our function has a name. So let's apply this to these two examples. Here we want to evaluate a function named f, that will be this function right here, defined as follows, when x is equal to 2. So wherever we see an x, we're going to put a 2 there instead. So we're going to have minus 2 squared plus 5, and remember, the no space here, that implies the multiplication, times 2 minus 3. And that will give us, well, negative 2 squared is 4. Negative sign in front of it, so we have negative 4 plus 10 minus 3. That's going to be 10 minus 7, or 3. So f of 2 will be equal to 3. What about this one? Well, once again, wherever we see an x in the definition of g, wherever we see an x in the rule, we're going to replace that with a plus 1. And remember that if there's no space here, that implies multiplication. So this is going to be 2 times the quantity a plus 1. Then the rest of the rule, which is plus 3. And then we need to simplify. We can distribute, and that will give us 2a plus 2 plus 3. Combined like terms, we have 2a plus 5. And there you go. Okay, now, we can also use alternate representations of functions to find out certain values. So here we want to find for two different types of functions the value of the function f when the input is 3. Okay, so take a look at this one. Here's the domain, that's the set of all inputs. This is the input, it's 3. It produces the output of 5. So in this particular case, f of 3 is equal to 5. Here is a graph of a linear function. Remember, this is the x coordinate, so this is the input. Here is our input of 3. We come up to where it intersects the graph, and it intersects the graph when the output is 4. So here we have f of 3 is equal to 4. One of the things that you're going to have to do in your homework here is to take an equation where x happens to be the independent variable and write it as a function. And how do you do that? Well, the first thing that you're going to do is you are going to solve the equation for y. Okay, and if you do for this particular case, you're going to have y is equal to 1 minus x. Once you've done that, all you do is just replace the y with f of x, and you're done. Okay, so in this particular case, the function associated with this equation is the function f, which is defined on the independent variable x, and its rule is 1 minus x. That's going to be the output. Okay, so let's actually do this in an example. Here we have an equation, and we want to write this in functional form. So step 1 is to solve for y. And to do that, we will have 4y is equal to x minus 5. Divide both sides by 4. And we have y is equal to 1/4 x minus 5/4. Almost said that backwards. In 2, we replace the y with f of x, and that will give us that f of x is equal to 1/4 x minus 5/4. Okay, and then finally we want to evaluate f when x is equal to -2. So to evaluate f of -2, wherever we see an x, we're going to replace that with a -2. So we are going to have 1/4 times -2 minus 5/4. That is going to be -2 minus 5 divided by 4, which is -7/4. There we go. We have that f of -2 is equal to -7/4. The last thing we want to do is to talk about the increasing, decreasing, constant nature of functions. Suppose we have a function f, and it's defined over some interval L, and we have these 2 points, x1 and x2, and they're inside that interval. Then we can say that f increases on L whenever x1 is less than x2, f of x1 is less than f of x2. And what the heck does that look like? Okay, well here's my interval. Okay, it's kind of straight. There's my y-axis. Let me change colors. And here is f. This is x1. This is x2. And as you can see, I could probably draw this a little bit neater, but f of x1, f of x2 is greater than f of x1, so we are actually increasing, as you can plainly tell here. When are we decreasing? And actually you can see we're going uphill. When are we decreasing? Well, when the opposite happens. If x1 is greater than if x1 is less than x2 and f is greater at x1 than it is at x2, then we are decreasing, kind of like what we have going on here. Okay, and as you can see here, as we go from left to right, we're going downhill on a decreasing function, and here we are going uphill. And then third, if it's constant, well, then the values don't change between x1 and x2. Okay, so that's basically the idea behind determining when a function is increases or decreases. So to make these decisions, what do? Well, we kind of basically look at the function and we ask ourselves, what does y do as x goes from left to right? If it's going uphill, you're increasing. If it's going down, you're decreasing. If it stays the same, you're constant. And the other thing you need to remember is that the concept of increasing and decreasing constant, they apply to intervals. They do not apply to points. So let's conclude with this particular problem or example, which, by the way, is a homework problem. Okay, so here we have the graph that shows the megawatts of electricity used in one day for one particular city. And we have to basically answer these questions, which is basically interpreting the graph. First one is to estimate the number of megawatts used at 5 a.m. Okay, well here's 5 a.m. Take the graph, comes up to here, and we hit 1,000. So the answer here is going to be 1,000. B is which hour between 0 and 24 was the most electricity used? Well, that's the maximum value of the graph. That occurs right here. And what value is that? Well, if I could stay on the same line, that would be helpful, huh? That would be 15. So that would be hour 15 or 3 o'clock. Okay, so we're going to call this function f. Okay, and we want to know what f is, what the value f is when the independent variable or the input is 12. Well, here's the input. That's 12. We can take that up. Hopefully I can stay on the line this time. And that goes all the way up to here, which is 21. So f of 12 is going to be equal to 2100 megawatts. And then finally, during what time intervals did the electricity usage increase? Well, for what time intervals are we going uphill? Well, this is when we're going uphill. And notice that we start going uphill here, that's at 3, and we stop going uphill here at 15. Notice here that, are we going uphill at 3? Or when we're at 3, are we going uphill? No, we're flat. What about 15? We're flat here. So the time interval is going to be the interval between 3 and 15, but it's going to be an open interval. So we will write it like that. And that is all I have for this particular video. If you have any questions, please feel free to reach out to me. This is Bob Boyle, signing off.